Hi, this is Brian Albright, Editorial Director at Digital Engineering. Thank you for joining us for the DE 24/7 podcast. Today, as part of our annual Technology Leadership Series, I'm joined by Matt Sederberg, CEO of Coreform. Welcome to the program, Matt.
Thanks, Brian.
Well, today I wanted to ask you some questions about Coreform's products and some of the problems they solve. But first, could you please maybe explain some of the challenges that you see that are presented by data interchange between some traditional simulation tools and CAD platforms?
Yeah, absolutely. So most of the people that we talk with at Coreform are those that are experiencing challenges with data interchange. If you're just doing simple simulations like linear static, I think that's a solved problem. There's a number of solutions out there where you can just automatically tap mesh behind the scenes and create a simulation and with really no issues. But as you get into more complicated physics or more complicated geometry, then data interchange sometimes severely limits the both the quality of the simulation that you can run, the number of iterations you can run, your ability to optimize designs. And that's for a few reasons. I mean, one is just the fact that CAD and simulation historically have been based on two completely different math definitions. So CAD, when it was started 50, 70 years ago, was based on NURBS and boundary representations, smooth splines.
Hmm.
And then simulation was built on Lagrange or faceted elements. And so they just necessitated data translation to convert from one mathematical representation to another. And that anytime you're translating data, you can lose fidelity. Um, Usually, you need to reduce defeature models, clean up CAD models in order to get a well-behaved simulation mesh.
Go ahead.
Oh, and this is just even exacerbated more with trends like 3D printing, where there's all these new, more exotic geometries, new mathematical definitions like implicit CAD, and so this just as advanced manufacturing techniques continue to evolve, the limitations of traditional finite element analysis are just becoming more and more pronounced as areas where people are more interested in running simulations. They're actually less able to leverage the traditional tools that have been made.
That's something else I guess I sort of wanted to ask about is we see a lot of non-traditional simulation users emerging in some of these workflows where there are folks who are using some of these tools that wouldn't have maybe in the past because of the way simulation is sort of working its way further and further into earlier stages of the design process. Is that sort of affecting this greater need for that type of interchange?
I think that's one of the pressures is the desire for simulation to lead towards actually analyzing and then optimizing the design. Too often in the past, and even still to the largest extent today, when you're running a very technically advanced simulation on difficult physics, if it's large scale like automotive crash or contact simulations, it takes so long to set up and prepare the model and then run it that by the time the simulation has been run, there's no longer enough time to make any optimizations and do anything with what you've learned from the simulation. And so it's more of a pass fail. Um, and so, yeah, the inability to have rapid, tightly integrated simulation tools at any stage of the design process is something that negatively impacts product speed to market and the development of optimal products.
Now, one potential solution, and one I know that Coreform is deeply involved in, is isogeometric analysis. Can you sort of explain for the listeners who may not be familiar, what that is and how that works?
Yeah, so it's a fairly technical term, but what it means is just that there's one geometry definition used for both CAD and for simulation. It's really, I mean, if you were to explain to your child like how things should work, it's kind of the obvious thing that if you spend a lot of time to create a CAD model, and that precise CAD model is used for manufacturing, you'd think that you'd use that same precise definition to predict how the manufactured model will behave. Um, and so this is a field, isogeometric analysis, that's really began in 2005 with some work published by Dr. Tom Hughes. And since then, there's been over 4,000 papers published at just this tantalizing thought that maybe there doesn't have to be two separate worlds of simulation and CAD. Maybe simulation could run directly on the CAD model. And so that is the software that Coreform is developing with our Coreform IGA solver. And our approach is unique in that we can allow all sorts of spline definitions and levels of placing the burden on the computer or the user to prepare the model for simulation. And so, as you were mentioning earlier, that there's a lot of demand for upfront simulation by design engineers, and there'll always remain a lot of need for simulation by PhD analysts. This isogeometric analysis paradigm is flexible enough that you can do fully automated simulations for upfront, or layer on additional kind of fidelity for higher quality simulations later on without needing to create a separate model.
Uh, yeah, since you mentioned the Coreform IGA, can you talk a little bit about how the product leverages, that analysis, and maybe sort of walk through how engineers listening might apply that in their workflows, what that might
Yeah.
look like?
Yeah, so the way that we leverage it is that we use higher order smooth splines to computer simulations. That's the same basis that is used in CAD. And we, as mentioned earlier, we have a full spectrum of allowing users to just automatically immerse the CAD model in this smooth spline, like in a bounding box, or we can create body fixed hex meshes and create a smooth spline from that conform to the CAD, or anything in between with what we call flex IGA, where we can have parts of the model that are completely immersed. You can think of like a tire simulation where we can have a bounding kind of tire shape, and then we can explore any amount of tire tread pattern designs inside of that without needing to create a conformal mesh for each of the tire tread patterns. But the way Coreform IG is leveraged today, we have a preprocessor called Coreform Qubit that is some of the best hex meshing software available, and you can create input decks directly in that software. As we've made some great advances over the last few years, we're now also developing a browser-based interface for Coreform IGA that where the meshing is not visible to the user,
Mhm.
that's more accessible for designers. And we're just excited about this ability to bring simulation more to the forefront, and make this really high quality isogeometric analysis accessible to a large number of engineers.
What, for engineers that are going to do this, what are some of the key benefits to using this type of product that you're seeing as you are, in the product development process, and that the end users can see?
Mm-hmm. I mean, there's the traditional benefits that anyone using simulation um, will generally achieve to some extent or another. I mean, the reduced time to market, the higher level of quality of products, the greater confidence that you could reduce the number of physical prototypes. I think where IGA really stands apart, though, is I was amazed when I came into this field how limited the frontier is of what types of simulations can actually be run. Like areas where that is especially pronounced is in new manufacturing techniques, where like for instance with 3D printing, as that is starting to become, there's more interest in having it go mainstream for mission critical parts. The issue is that you can't run a highly accurate stress simulation on any 3D printed part of complexity. And so that means that you're resorting to physical testing, which is not scalable and difficult to optimize designs like that. But with isogeometric analysis, the need to not create that detailed mesh, but to be able to use the design data directly as the representation for simulation means that you can simulate very intricate 3D printed parts. Um, and basically anything where there's geometric complexity. So tires is another interesting area where there's a lot of interest in creating airless tires, but that leads to the need to create a much more complex geometry to support the structure of the tire while also allowing for enough air to flow through to cool it. And that again will tax what traditional FEA tools can do. With isogeometric analysis, again, there's no limit to the complexity that you can add to the data that will be simulated in IGA.
It's sort of a follow up. How else has the emergence of these alternative manufacturing technologies like 3D printing and even the way 3D printing has sort of affected some of the other manufacturing environments, how it's being used to work in conjunction with molding and machining in some cases. How else has that sort of affected the environment that your customers are in that sort of make this tool more appealing?
Well, I think what that does is that it, um, like the days of being able to just have a simulation tool that only accepts a very nicely behaved like type of data, whether it's a hex mesh or a tep mesh, and it has to be precisely created specifically for simulation are over. I mean, beyond the new geometry definitions for 3D printing, there's been an explosion in the amount of scan data that is now a part of the design process. And you see the CAD kernels now are creating these hybrid kernels where they can accept smooth boundary representation data, analytical geometry, scan data, but the simulation kernels have not kept up with that and still require a very specific type of element. So with isogeometric analysis, our solver is broad enough that we can accept scan data directly. We can accept CAD, traditional CAD data, implicit CAD, and so it really just mirrors where CAD already is, and it brings the simulation world to a point where simulation is not the separate thing done in a completely siloed area, but that it can be deployed throughout the entire CAD development process.
I like that you characterize the data as being well behaved. I guess the alternative would be having naughty data coming in from
Right. Yeah,
other
you want
sources.
that.
All right. Well, thank you very much for your time, Matt, and thank you for joining us on the podcast.
Thank you so much.
All right. Thank you all for listening, and we'll see you next time on the DE 24/7 podcast.